built motors with different numbers of poles and phases. Some companies spent years developing special copper alloys or aluminum mixtures. Others tried superconducting materials that only work at extremely cold temperatures. Maybe the solution isn't better metal at all. What if the entire approach was wrong from the beginning? What if motors could work without metal coils completely? This sounds impossible because electricity needs conductors, and conductors meant metal for over a century. Korean scientists asked a simple question that changed everything. What if motors didn't need metal coils? They wondered if some other material could conduct electricity just as well as copper, but way much less. This question led them down a completely different path. Instead of improving metals, they started looking at carbon. That question led to a laboratory breakthrough that could eventually force engineers to rethink motor design. A fundamental shift, not an instant swap. But what they discovered challenges everything engineers thought they knew about making things move. The carbon revolution that changes everything. The answer came from something thinner than human hair, but stronger than steel. Millions of carbon tubes working as one. These tiny structures, called carbon nanotubes, measure just a few atoms wide. Each one looks like a rolled-up sheet of carbon atoms formed into a perfect hollow cylinder. The walls are only 1 atom thick, yet these microscopic tubes conduct electricity better than copper while weighing much less. Carbon nanotubes work like tiny electrical highways. Electrons flow through them with almost no resistance at all. In early tests, these aligned carbon cables showed conductivity improvements of roughly 130% compared with copper. Think of it like comparing a smooth superhighway to a bumpy dirt road. Electrons zip through carbon nanotubes without getting slowed down by obstacles. Copper atoms create roadblocks that waste energy as heat. Carbon atoms line up in perfect patterns that let electricity flow freely. Here's the challenge that stumped researchers for years. The question researchers faced was how to produce millions of these microscopic tubes in a way that was practical and scalable, to line up perfectly and work together. Individual carbon nanotubes are amazing conductors, but they're incredibly tiny and tend to tangle up like microscopic spaghetti. Getting them to face the same direction and stick together seemed impossible. It's like trying to organize millions of invisible threads while wearing boxing gloves. Scientists developed a breakthrough process called LAST that solves this problem. LAST stands for Allotropic Liquid Crystal Assisted Surface Texturing, a process that lines up millions of nanotubes so they act as one conductor. This process forces millions of carbon nanotubes to align like soldiers standing in perfect formation. The tubes line up parallel to each other and stretch in the same direction. They create a sheet of carbon that looks almost like black fabric, but conducts electricity better than any metal wire. The process works like this. Researchers grow nanotubes, then use the last process that aligns them into a continuous core. Chemistry and tension lock them together into a flexible cable. The result is a flexible sheet made of millions of perfectly aligned carbon tubes. Next comes the protective layer. Scientists wrap the carbon nanotube core with something called a CCEC sheath. CCEC stands for Core Sheath Composite Electric Cable, which creates a carbon nanotube core wrapped in a protective sheath so the conductor is flexible and insulated. This protective covering works like insulation around a regular electrical wire. The sheath keeps the delicate carbon tubes safe from damage while letting electricity flow through the core. It also makes the final product flexible enough to bend and twist without breaking. This creates something remarkable, a bendable, twistable conductor that carries electricity perfectly. Unlike copper wire that breaks when bent too much, these carbon conductors flex like rubber bands.